morning, everybody, and welcome on the last session this year on basics of video technology. So last time we stopped at this example here. Basically, we saw how we can take bits which represent indices of our quantizer and take pairs of bits, 2 bits each, and write them into a file by simply grouping them into bytes. Right? 4 pairs make 8 bits, so that we can store them in a file using the Python commands for file access. And we had this example here, write, read bits. So maybe I can just open it, copy, and examples. No, edit. So here you can see that we have the functions that we need for reading and writing the file. So here, this is the function for writing a binary file. So it takes as the input the file name here as the first argument, and then the bit string, which in our case was a string containing zeros and ones, and then those zeros and ones are turned into real bits for the file, which you can see here. So basically here we do the conversion, group them into bytes, and then we can convert those bytes into real bytes for our file, and then write it here in this line. So in line 34 we do the actual writing, in 32 we open the file, and then in line 35 we already close it. So basically we just take our string containing zeros and ones. At the end of the function we write the entire string to the file, and then we close it again. Make sense? So these are the usual file access commands of Python. So in read binary file, as the name says, this is reading from a file. So here we can see in the beginning we open the file and then read the content. So here this file read in line 47 basically reads the entire file, not just chunks, but the entire thing, for simplicity here. So if you want to have a really large file, then you would read it in chunks. Right? But here it's more like a demo, so here we can read the entire file. So then we do the reverse steps. We take the real binary format and turn it into something that Python can more easily read. So bytes read in this case is integers, and then we turn those integers into binary string again using the function bin. So bin basically turns our integer number into a binary representation, basically our string. So here we fill it with leading zeros, because we also want to have the zeros in the beginning, and then we concatenate everything, and then we return this bit string in the end. Right? So here's the reverse. Yeah, so the data to code string is simply taking our indices and turns them into a string of bits. So here you can see the conversion. Here this is our code words, so it takes an index 0, 1, minus 2, minus 1, and turns it into a binary representation with 2 bits each. Right? So this is basically our encoder, turning integers into binary words. Yeah, and those binary words are basically sequences of zeros and ones as strings, and here we concatenate them here in this for loop. So out comes the code string, which in the next step we would write into file. And here the other way around, in the decoder we have code string to data. So from the file comes code string, and then we need to turn this code string back into a sequence of indices, which you can see here. So here's the decode word dictionary. So in goes our binary word, out comes the index, right? 0, 1 or minus 1, minus 2, here in line 98. And we do this conversion again in a for loop that you can see here. So in goes the code string, the sequence of strings of zeros and ones, and it takes pairs, and each pair represents a code word, and this is then converted back to an integer. And then it returns the data. So data now contains our sequence of integers. Make sense so far? So you can see it's mostly conversions and reading to and from the file. And from the theory, the most important part here is the tables. So here we have the decode word. This is the table turning the code words back into integers. And in the encode string, we have this code word table turning our indices, the integers, into code words. Right, so this connects binary code words to our integers or indices. Yeah, then I have this little test routine here, which we now want to try. So when you wrote a program, it's a good practice to have a testing routine. So I usually always add this main routine, which says if main, then do this. And this means this is only executed if you call it from the terminal shell directly, but not if you import this file as a library to other functions. So if you want to use this as a part of a coder, for instance, then you would say import write read bits, right, the name of this file. And when you say import read write bits, then it doesn't execute this main part, because in that case it's not executed from the terminal shell. Does that make sense? So I'm usually using this if main section for testing. Right? When you're done with the functions, then you can easily add a short testing routine, and when you call this file directly, then this testing routine is executed. So that makes testing more convenient, because you can more individually test those functions. Yeah.
You need to call the functions under the if main section. The functions defined.
Yeah. So when you say this if main, that means this file was called from the terminal, and that means all the functions that you defined above are there, right? So when you call them with this name, they are recognized. Right? Unlike when you say import read write string, then you have to prepend read write string dot function name. So here write read bits. Right? So it depends on if you import it as is, or if you import it like with a short name, like import numpy as np, then you would specify each functions of numpy as np dot something. You could also use from name.py import star. Then you don't need to have any namespace, but this is not what I'm recommending, because that can be confusing. It's always better to have a name for the file that you're importing. Yeah, so here you can see it. I'm defining some data, some fantasy data in this case. So just a sequence of indices. So these indices should come from our quantizer later. Right? So our quantizer produces those numbers between -2 and 1. And here just took some more or less random numbers in this range for testing. Right, so here we have eight indices that comes from our quantizer. And then the next here I define the name of our file. So for testing I just use the name savebin.bin. You could use any name, but it's also good it's good to give them a name which says something about the file, so that you later less confused, right? So if you have something .bin, then you know it's a binary file and not a text file. So that's why this .bin is a good agreement here. So then I call the first function to test data to code string. Right? Remember, data is our sequence of integers which represent now our indices. And now this data to code string calls our code table and turns each index, each integer, into a pair of bits as a binary representation. So what comes out of this function is this code string, which we then print to check if this function did something reasonable. So we can check if we really have those pairs of code bits. Next, we write it to a binary file using my function write binary file. So both are defined above in this file. Right? So we can access them here without prepending the namespace. Here I give it the file name, the savebin.bin, and here I give it the code string which we just computed using this function here in line number 121. So now we wrote it, and now we can actually check the size of the file. So how many bits do we expect to have in this file, savebin.bin? This is actually also good for checking. Right? It's easy to see the size of a file, and it needs to have the size that we expect, otherwise something would be wrong. So how many bits should this file have? Right, how many indices do we have? No?
Look at 8.
Yeah, 8 indices. How many bits does each index have?
2.
Right. Remember, each index had 2 bits. Because we only have 4 possible indices, we need 2 bits to represent them. So how many bits in total would we have in the file? No?
16 for the data. I'm not sure.
No.
There was something where we prepended leading zeros. This would only be the case if we don't have a whole number of bytes, then we would prepare zeros to fill it up.
Yeah.
Okay.
Excellent. So here we have 8 indices, 2 bit each. That means we get 16 bits, right? 8 times 2. Does it make sense to everybody? 8 code words, each code word has 2 bits, such that we have a total of 8 times 2 bits, 16 bits. And this fits nicely into a byte, right? So we don't need to fill up anything. So we have actually 2 bytes. 16 bits, 1 byte is 8 bit, so we have 2 bytes. So when we take a look at the created file in our file system, we should see that it contains 2 bytes. Right? If it's not containing 2 bytes, then we know that something is wrong. So this is also important for checking. Yeah, the next step here will be to read those files back from the file. Right? This would be the decoder. The decoder needs to recover the file that we stored in this file in the first place. And for that we use the file read binary file, and as argument give it the file name. Make sense? So then it returns our code string. So again, this is a string containing the zeros and ones. And we can actually also check it after we turn, well actually code string, yeah, code string contains the zeros and ones. Actually it would be nice to actually print it here. Print, so let me add a print. Code string, decoder equals code string. So then it prints our code string, and that should be identical to the code string here in the encoder. So maybe I should say encoder. And next it turns this code string back into a sequence of integers, which represent our indices. And so finally here we can print our indices, the data read, decoder. Right. So here we have the data, we should just call it data decoder. Makes sense? So we have two steps in the encoder, which we see with the print. We have our original indices as integers, as the numbers. Then we have the resulting bits as a bit string. Then it creates a file, which we can check in the size. You could also look into it using the command OD, for instance, for octal down. We can actually look at the content, the binary content. And then next step, we have the decoder, and we can see if the code string was successfully recovered. It should be identical to the encoder code string, right? And then we have the recovered data, the indices, which should also be identical to the encoder. Yeah. Make sense? So then we can actually execute it and see what we get. So here now level 1. Let's see if it works with Python 3. Here. So here you can now see the output. First line, the data. This is our example data. Right, there's more or less random numbers between -2 and +1. Then in the next line you can see the code string in the encoder. This is the resulting string of pairs of bits which represent those indices. So they come out of our coder table, the code table in the encoder. Then in the decoder, so in the next line is already after reading from the file. Yeah, what do you think? Is it identical? Yes. It should be identical. If it's not identical, then we know we have a problem. But here it's indeed identical. It's just shifted a little for some reason. Then here the data in the decoder, is it identical to the data in the encoder? It looks good, right? It should be identical. So maybe I should call this data encoder to roughly bring it in the same position. So now, how do we check the size of our file? So here we have the file save.bin, and we want to check that it indeed has 2 bytes. How do we do that in Linux? Everybody should know Linux by now, right? So, which command do we use in Linux to check for the size? Do you know the command ls?
Yeah. Yes.
List. Right? ls gives you the list of files in a directory, and ls -l for long gives you the size together with the file names. Right? So you use ls -l and then say save bin.bil. So in this case, it just looks at this file with this name, and it lists information that it has for the -l output. So when I say return, this is what we get. So here you see the access rules, read-write, for user group, and for others it just says a read. Then here the username, which is me. Then here the date and time of creation, which is December 16. Yeah, that's correct, right? at 11:22. Yeah, it should be right. So this is for checking that this is actually the file that you just created, right? Not some old file which might be left over. So this is current, and here the 2 is the size, 2 bytes. So this is actually always the size in bytes. So now we have our confirmation that this is indeed just 2 bytes. So this is actually really a tiny, tiny file. Usually here you see something with K or M, then it's kilobytes or megabytes. Here there's no K or M because it's just bytes, 2 bytes. Right. So this now also confirms that it corresponds to our expectation. So no obvious error at this point either. So it seems our system is working. And this is actually the testing that you should always do on your programs before you actually use them, because finding errors in a larger system is much more complicated than finding the errors in your original small functions. And before you use a function somewhere, you test it, like this. And so that's the usual approach for making software. Make small functions, test them immediately before using in a bigger system. Otherwise you get strange problems maybe later, and then you spend days and weeks and months to find the problem. And maybe then that's the source of a security vulnerability of some larger system, for instance. Right? So security vulnerabilities are always a problem of not enough testing somewhere. Yeah, so this is what we now just did. So now we can actually apply it in a simple encoder and decoder for a frame. Right, so I have an encoder which takes the lowest 3 DCT coefficients at position 0, 0, 0, 1, and 1, 0. So this DC, and then the nearest AC coefficients horizontally and vertically. Right. Make sense? So 1 DC and 2 AC coefficients. And yeah, so this is actually quite similar to the quantization experiment which we did before. Remember, where we also quantized the DC and the AC coefficients differently. And we saw that those 3 coefficients are not really enough for good quality reconstruction, but you could see the image content. So you could still recognize what's going on. So here, for simplicity's sake, we define our 8x8 pixel blockwise DCT and inverse DCT by functions. So to make the code more easily to read. So I basically encapsulated them into functions. DCT 8x8 and DCT 8x8 in the file block dct.py. So I basically separated them out. And this is also practical for reuse in other programs. Yeah, and the size of the frame that we want to encode is additionally written in a text file for the decoder. So when we just have a sequence of indices that we just saw, the decoder needs to know how to arrange them, in what format of picture. And this is what I did in the simple text file to make the program easier. So I keep this information separate from the binary information. Right. So here's the file, which we can now take a look at. Copy, edit. So here you can see the file. So here we can see it imports this block DCT, which contains the 8x8 DCT functions. And then it opens the video capture as usual. using OpenCV. Then it reads the dimensions, rows and columns. And the first thing it does is to write this information into a text file framedim.txt. Right? So it just contains two integer numbers, R and C, for the decoder. Yeah, and then here we define our DCT, n equals 8, and here's the infinite loop. Here we read a file and create the Y, the luminance component, as usual. So we take the black and white image. Here we have our weight key, and if we press the key C, it applies the DCT here. So basically then it's doing the compression. So here, when I print the C, it actually takes this frame like a photo and stores it after compressing it. C for capture or compression. So basically uses those files. So you can also see I'm using Y00, Y01 and Y10 to encode the indices of those three components of the DCT. And I'm using, again, different files to make the program simpler, because then we don't need to program the interleaving and de-interleaving of those coefficients. So it doesn't have to be different files, but just for the sake of simplicity here, I'm putting them into different files. Make sense? So each DCT coefficient gets its own file. Yeah, so next I'm applying the DCT 8x8 to our frame, the Y frame. So X now contains the DCT converted coefficients. Now I'm doing the quantization as last time with the quantizers. So here bits equals 2. So again we take our 2-bit quantizer and 2-bit encoding. Here the step size for DC, so this has the range of 5 as last time. Here we are doing the mid-thread quantization. So here DC, we subtracted 2 to be able to use the same code table. Right? So here we are also using the values from -2 to +1. And since DC has no negative values, I'm just subtracting the middle value here, the -2, to get the same value range. Yeah, so this is still of the shape of our image, and here I'm reshaping it such that it is just one row. Right? It's one long row, because this is how we store it into file. Yeah, and then we take those indices as one long row and put it into the function data to code string, which you can see here, and this generates the code string. And then we take this code string and write it to file using our function writeBinary file. So now we have the function the file y00enc.bin. Right. So basically the same sequence as we had before, now applied to real image. So now we do the same for the two AC coefficients. Here we don't need to subtract anything because the AC coefficients are already negative and positive. Right? So here we can take our original encoder unchanged, which has this value range from -2 to +1. Here we have a range of 1, so values between -1 and 1. Here we do the mid-thread quantization using rounding. Here again reshaping and writing to a file, converting to code string, writing to a file, here with the name y01. And then we do the same for y10 here in this point here. Right. Does it make sense so far? So basically the same as you just saw in our little test, but now applied to those 3 DCT coefficients for our image. Yeah, and here we display our black and white image, put information as text on it, and then we are done. So basically this is just like a camera, right? It takes one frame when you hit the button C, and then it's done. Then you can close it using the key Q. So let's see. So it takes my little webcam here, so I can try it. So Python 3. So now you can see here the black and white image. So now it waits for me to hit the key C. So C is the capture. So let me try C. So the only thing you see that it did something here, right, in the terminal. So now I say Q for quit. And now we can again see what kind of files it generated. Again using ls. Right. So you would say ls minus l. And what file names do we look at? Something with y dot bin, right? So y star. I guess everybody knows what the meaning of the star. So star means anything, right? So anything that starts with a y and ends with dot bin is now listed. So here we can see it. So what's the ones from today? We can actually also list them by temporal order, LT. Do you know LT? T means it's listed instead of alphabetical in temporal order, so that you get the newest entries first. So this is what we need now. So here you can see December 16, 11:36, that's about now. And here you can see we have 1200 bytes. So this is a lot more than 2, right? So why is it so much more than 2? No?
Our image contains significantly more data
No.
than just a couple of numbers as we had before.
Right. So y00 now contain y00 or the other ones, they contain now the AC coefficient for all the 8x8 blocks of the entire frame. Right. So how many coefficients do we have now in here when we have 1200 bytes? How many indices does this correspond? How many indices does one byte contain? And remember, each index is 2 bytes, 2 bits. Right. So if one index is 2 bits and 1 byte is 8-bit, how many indices fit into 1 byte? Yes, very good. So it's 8 divided by 2. Make sense to everybody? So how many indices do we have now in each file? If you have 1200 bytes, how many indices is that?
600.
Really? Why? 1200 bytes. Yeah. So how many indices is 1200 bytes? No idea? Yeah.
4,800.
Yeah, it's basically 1200 times 4. Right? If each byte has 4 indices and we have 1200 bytes, then we need to multiply 1200 bytes by 4 indices per byte. So it's also like a unit, right? You have indices divided by bytes. And you have bytes. And then when you say 1200 bytes times 4 indices divided by bytes, then the bytes cancel and what you're left with is the indices. So this is basically what you should know from physics. Units you can cancel. These are not really units, but you could treat them like units. Make sense? So here we indeed have 4,800 indices per coefficient phi. And this comes from the size of our frame. Again, we have this VGA size frame. Yeah, so we successfully generated our files, and the sizes kind of look okay. I mean, I didn't really compute what exactly we expect, but it roughly sounds okay, because we need to do the downsampling by 8 horizontally and vertically. Right, so it's a factor of 64 compared to the total number of pixels. Yeah, so next we need the decoder. Oh yeah, so first we can take a look at the total number of bytes. So we have 1200 bytes for each of those 3 files. So that gives us a total of 3600 bytes for one frame. Right? 3 times 1200 is 3600. So that's 3.6 kilobyte. Yeah, and 3.6 kilobyte for an image is actually extremely low, right? What do you usually get when you take a picture with your camera? How many bytes does it have? In your experience? Yeah.
For JPEG, it's usually something around a few megabytes. For RAW, it's significantly more, of course, but JPEG about 1,000 times as much as this.
Did you other guys look at the size of your images from your camera? You never look at the size of your images? You just wonder why you... Huh?
It's just a little megabytes.
Yeah, it's a few megabytes, right? And the point is that's an order of magnitude more than this. Right? This is not megabytes, this is kilobytes. Right? A megabyte is 1,000 kilobytes. So this is about a factor of 1,000 less than what you would expect from usual camera pictures. So this is kind of suspicious, right? It's too good. Just 3.6 kilobyte. So it's an extreme compression even for a VGA image. So VGA is 480 times 640 pixels. So we don't expect much in terms of quality, right, when you have so much compression. So then we can take a look at the corresponding decoder. So let me just open the decoder here. Copy, gedit. Here's the decoder. So the decoder basically takes the reverse steps. So it first reads the files that we just generated. I gave them fixed names again for simplicity. So here I'm using this read binary file and then the code string to data to get my indices back. Here for the DC part I have to add the 2 because I've subtracted the 2 in the encoder to get the original value range. Here I'm doing the same for the AC bits, except that I don't add anything. Here I'm reading the dimensional file, the frame dim.txt, to get the number of rows and columns for reshaping. So then I'm just taking those indices, reshape those indices in the shape of our image, right here in the rows 37 to 39. And then I apply the dequantizer. So here is the reconstructed image, which I initialize with zeros. And now I'm assigning the dequantized indices to the corresponding positions. So here we have the DC quantization step size, here the AC quantization step size, and here I'm doing the dequantization by just taking the indices and multiply them by the corresponding step sizes. And here I'm already assigning the right positions. So here you can see the DC coefficients are assigned starting with position 0, 0, and then going up by n. So in this case 8. Right? So they appear in each block at the position of the DC value. Make sense? So this is the purpose here of this upsampling of the indices, that the AC comes at the upper left-hand corner on each block, on each 8 by 8 pixel block. And correspondingly from the DC coefficients, starting at position 0, 1 in the upper left-hand corner, so that's the one next to the DC, and then repeating in every block of 8 by 8 pixels. Again here, every 8th sample is assigned. So after we assigned all the dequantized values, we have now blocks of 8 by 8 where we have 3 pixels assigned values. The upper left hand 3 pixels. So what's about the remaining pixels? What values do the remaining pixels have? Or values, not pixels yet. So far we just have a matrix of DCT values. So for each 8 by 8 block of DCT values, the upper left hand 3 values are assigned. What about the rest of the values, which are not assigned? No?
They're 0 because we initialized our X-ray matrix to 0 is in the third line.
So that was, where was it? Here. Does everybody see this? So if you're not assigning anything, it's 0. Right? So again, it's convenient. Yeah, and after we assigned all the dequantized values, I apply the inverse DCT to the 8 by 8 blocks to this XREC matrix. And then X, lowercase x, now contains our decoded image. And then here, in this infinite loop, I'm just displaying this recovered image until I hit the key Q and then it finishes. So here in line 66 you can see it's displayed. Makes sense? So now we can execute this file. Python 3. Yes. See? This is the reconstructed. Oh. Let's go. This is the reconstructed image. Nice, isn't it? Well, maybe not so nice. Huh? It's a little bit artistic. Right? You can see it has lots of blocking artifacts because we only used 3 out of the 64 coefficients in each DCT block. And it also has artificial boundaries because of the quantization with very few steps. But you can still recognize that it's me in front of a board, right? So despite only having 3.6 kilobyte, the picture is still recognizable. Well, it's actually quite nice, right? We have a functioning compressor now. And if you think that this is like a little icon, for instance, then you wouldn't even notice that it's having those blocking artifacts. Oh, makes sense? So now I can quit it with the key Q. Yeah, so here's what I just said. There's only a few shades of gray as a consequence of extreme compression, but we can still see the content and recognize the content of the picture. So, yeah, now the next step is to include color. Right? So far we just applied the scheme to the Y component, the luminance component, but usually we want to have color images. Right? So now we also have to include the CR and CB. Right? Here, U and V or CR and CB. And we can simply do that by applying the same scheme here also to the color component. But we know that the eye is less sensitive to the color component, so in this case, we could just take, instead of 3 coefficients from the DCT, we can just take 1 coefficient, right, to limit the overhead for the color. Right. Yeah, so we limit ourselves to coding the DC coefficients of the CR and CB, or Y and U. Yeah, and because now I'm creating even more files, I'm creating a subdirectory here for this picture, and then I'm executed inside this subdirectory. So first we can take a look at this file here. This is my encoder now. Copy, gedit. So here, this is now my color encoder. Basically, it starts with the same commands. Here it stores the size in the beginning, and then it takes picture. Here, this infinite loop. But now it not only computes the Y component, but also the U and the V component that you can see here in lines 45 and 47. Right? So 2 color components. In this way that is defined, for instance, in analog TV by just taking the blue and the red component and subtracting Y. Yeah, then it applies the DCT, the 8x8 block DCT, to each component, the Y, the U, and the V. So now we have 3 pictures. And here it just prints out an example value of the DCT for color component U, the minimum possible, so this should be a negative value, because color components can be negative. So then we define again a quantization step size for DC with the same range. And here we have the coding of the DC component of the Y component stored in the same name of the file, Y00 enc, but now C for color, so that I don't overwrite the other ones. Here now again the 2 AC values. So here 0, 1 and 1, 0. And now the color components. So here again, same quantization step size. I could have a different step size here, but turns out the same step size is sufficient. And here I'm doing the quantization. And here I'm also don't need to have this -2 because DC of our U and V component can also be negative. Yeah, so here I'm reshaping, coding, and writing to U00. And then the same with V, with the V component. And here writing to V00 enc. Make sense? So basically we do the same as in the Y component coder, just that we now have 2 additional components, 1 DC value for U and 1 DC value for V. Right? And we can do that because we know that the eye has reduced resolution for color. So here instead of having 3 coefficients, we just use 1 coefficient, the DC coefficient. Yeah, so here again pressing C means I'm taking the picture, and then with Q I'm exiting the program. So here I can go to CD picture, say make the pick 3, pick 4. So I'm now creating a new directory for a new picture. CD pick 4. And now I can execute my little program. And Python 3, but since it's one directory up, I need to use this notation. Are you familiar with this dot dot, the meaning of dot dot? So dot dot is one directory up. Right. So now I went down to pick 4, but my program is one directory up, so I have to use dot dot for the directory up, and then that's where my program is located. So now I'm executing it. Go. Seems I need to adapt it for Python 3. Yes. So you can see it. So now it's color, not just black and white. Right? So now I can take capture. Yes. So now I took a picture. And you can see I took a picture by looking at this printout, which tells you which frames are generated. And you can also see this number here. This is the most negative value of our color component U. Right? And you can see it's indeed negative. So now we can take a look at the resulting files. So here you can see them. So the Y coefficients are there, but now also U00 and V00. So these are the DC coefficients of the two color components. So again, each with 1200 bytes. So how many bytes in total do we now have in our color picture? We have 5 times 1200. Right? So it's about 6,000. Actually 6,000 plus 50, but I neglect those 50. So we have 6 kilobyte here. So about 6 kilobyte. And if you divide it by the number of pixels, then we get 0.16 bits per pixel. So that's again extremely low. Right? So we have an extremely good compression here, but of course we sacrifice quality. Right? When you think about 6 kilobyte, again, a factor of 1,000 less than usual photos. Yeah, and then we can start the corresponding decoder, which I do here. So I'm not looking into it because it's basically the same principle. So here's the decoder. Wow. It seems the color is a little bit off, huh? And the board is not really green. So why is the color off here? What do you think? Why do I have a pink face and not a real color of skin? And it's again, yeah.
You want to say? Due to the artifacts.
Yeah, why do we have those artifacts? And it's the quantization, right? So remember, here the color components, they determine the color, and I quantize also the color components with only 4 levels. So that means for each color component, I have 2 color components, each has 4 levels. That means we have altogether 4 times 4, 16 different colors possible. Right? And this is just one of the 16 possible colors. So that means the colors are not really true because it's too few. But at least it's color, right? Okay. So maybe I can take also a look at some previous pictures I took. So here's pick 3. And you can simply apply the same coder. So this is some previous example that I took last year. Right? So here you can see there's a little bit more color. You can see the seats here, and you can see the ceiling. But again, you can see the color is not really true. I mean, it's kind of right. It's not totally wrong, but it's a different hue. Right? It's not really fitting so well. So this happens when you do too much quantization on the color components. So this corresponds to the artificial boundaries when you quantize the luminance component Y. When you quantize the color components, you get wrong colors. And the human eye is particularly sensitive for face color. Like in my case, like this pinkish face color is something that people pick up very easily when you have the wrong color in the face. So actually here it's not so bad, maybe because the faces are so small, but if you make errors in the face color, this usually creates obvious artifacts. And this was, for instance, also a problem with the original analog color system, NTSC, which came out of the US. They had this phase changes, possible phase, which we saw in the beginning, I guess. And if you have those phase changes, then this results to wrong kinds of colors, and this is in particular obvious for face color. Okay. Yeah, so this is kind of an artistic image in appearance, but still the image content is clearly visible and recognizable. Yeah, so quantization here is actually crucial, and we saw that the contrast sensitivity function gives us a good hint about what quantization step sizes to use. Right. So here the contrast sensitivity function. So here it is again. So here we have the spatial frequency and cycles per degree, and vertically is the sensitivity. So it means if the curve is higher, the eye becomes more sensitive, and we need to choose smaller quantization step sizes. And here for the cycles per degree, we need to have some conversion to the subband index, right? So that we know the subband index is somewhere in this image. And this conversion, remember, depends on the resolution of our display and the viewing distance. So basically how many pixels per degree we can see. Yeah. So when we have an 8x8 DCT, that means the lowest band is actually quite wide, and it ranges to the maximum of this curve. So here basically that means the lowest subband here, DC, goes up to about here. And here it becomes more narrow because we have a logarithmic scale. So that means the DC value needs to have the most bits, or the finest quantization step size. Yeah, so here the most accurate quantization for the DC value. And that also means when we go to higher frequencies, higher spatial frequencies, then the eye becomes less sensitive or increasingly insensitive. That means you can quantize them more coarsely. So, since we have two dimensions for our spatial frequencies, horizontally and vertically, again for simplicity, we just assume that if we have a constant sum horizontally and vertically, that represents the same spatial frequency overall. Right? It's not true exactly, but roughly. And again, it's for simplicity. So here S equals K plus L. The sum of the two indices, subbands horizontally, vertically, gives us the cycles per degree for the CSF, or for the computation of the quantization, or for the quantization step size. Yeah, that means we select the same quantization step size for each of those subbands which has a constant sum. So we have the same quantization level because they correspond roughly to edges of the same slope in the different directions. So this results in antidiagonals with the same quantization step size in our quantization matrix. So imagine we have a matrix of the size 8x8. Each entry of this matrix contains the quantization step size of the corresponding DCT coefficient. And so basically quantization is done then by taking the DCT matrix, divided by this quantization matrix, and do the rounding. in element-wise division. Yeah, so at the top left is the DC value with a highest accuracy, which means low quantization step sizes. Down to the right, towards high spatial frequencies, the accuracy becomes smaller and smaller, which means we will get higher quantization step sizes. So this will give us a more detailed quantization mask, and to make it in Python we use the command npdiag, because that produces diagonal matrices. And we can also give the diagonal a given offset from the diagonal. So that's very practical for quantization matrix construction. So for instance, here we can see B is this matrix which contains 1, 2, 3 on the diagonal. So you can see 1, 2, 3. Right. So it just makes a zero matrix where we have those values from the argument on the diagonal. And to make it anti-diagonal, we can just use flip. Flip LR, flip left right. So here you can see the result. The last row is jumped to the next page. So it's basically the first matrix flipped left right. And then we have this anti-diagonal shape here going backwards down. And this is what we need for our quantization step sizes. Remember, the anti-diagonals should have the same values. Yeah, and then we have the command trill, which means triangle lower, and this generates a matrix which is filled up on the lower triangle, as you can see here. So this creates a matrix of size 4 by 4, and it fills the lower triangle, but up to the first diagonal above the diagonal. So this is what you can see here. So here is the diagonal, the original diagonal, and then here we go one up. So here the second argument tells you how much up the ones will go. So basically this is used for filling up the quantization matrix after flipping it. So again, we can also flip this to get anti-diagonal shapes. Make sense? So this is how we can make quantization matrices which have the same value on the anti-diagonals. So here we have the different quantization step sizes. So now we're using 4 bits for DC, 3 bits for the next anti-diagonal, which now really is a diagonal because the DC is just one entry. So here we have then 2 entries with 3 bits, 3 entries with 2 bits, then 4 entries with 1 bit, and the rest is just 0, which means you just choose some really large number. So, and this is this number is also the expected range of values for the different coefficients. And this is again what I found by looking at typical images. Because this is yeah, it's better to have a smaller range where you are sometimes exceeded than to have a full range and bad quantization. Yeah, so questions to this part here? If you code, you can close the window. Yeah. Right, so the 5, the 1, the 0.4, and the 0.6, they basically came from looking at images and see what range we expect in those coefficients. And the last one here is basically just a large value which rounds everything to 0. Right. So that means we have, for the DC we have 1 times 4 bits, then for the next two AC on the next anti-diagonal we have 2 times 3 bits, then 3 times 2 bits, and then from 4 times 1 bits, it's together 20 bits for 64 pixels. And that results in a total of 0.31 bits per pixel. Right. So it's still rather low. It's still good compression that we get. So here we now making the actual quantization matrix. So we initialize with zeros. Then here's the DC value. And now we are taking the flipping of the diagonal here, and we shift up the diagonal 6 places. And here we multiply it by quantization step 2. So here we have the 2 ones multiplied by quantization step 2, which was the 3 bits, corresponding to the 3 bits. And then we do the same for the next anti-diagonals. And then we use the flipped triangle lower for the remaining matrix. Okay, so the rest is filled up with some large numbers. So here you can see the first 3 by 3 entries. So here's the value for DC. You can see it's rather small. Here the next anti-diagonal is the next larger numbers. Here's the next anti-diagonal. 3 values. It's again larger. And then the rest is filled up with values of, well, this is then the next anti-diagonal which has 8, and this is the remaining, which is 800. Right. Does it make sense? So I guess I could also copy and paste and look at it in Python. So I could say Python minus pylab. Maybe I don't need to plot. Import numpy as np, and then paste everything. Oh, on step 1 is not defined, of course. First I need to define the quantization steps. Copy. Okay. Yes. So here you can see the matrix completely. Maybe you cannot see that much, but you can see here the lower values are all 800. Can you see that? So basically, the rest is all filled with values of 800, which basically has the purpose to round everything to 0 in these frequency ranges. Here's the DC value, then here is the next diagonal. Here, the shape is kind of unfortunate. Yeah, so everything is on this anti-diagonal. You have the same values on each anti-diagonal. Yeah, then we can apply this matrix to each 8 by 8 DCT block, and each DCT coefficient is then divided element-wise by the entry in the quantization matrix. Yeah. So right and down we have the highest spatial frequencies, and that's why we get higher and higher quantization step sizes. Right. So here is what we just saw. We got this 0.3 bits per pixel in this way. So we get more than before. Before we had 0.1 something, but we should get better quality. Yeah, so here we filled it up with this triangle lower. And we need to apply this mask to the entire image, right? Remember we had this mask for one 8 by 8 block of DCT. So basically we need to repeat this now for the entire image of the size of our VGA image. And this is what we do with the Kronecker product, NP Kron. Have you heard about the Kronecker product? Yeah, this is kind of a little bit more exotic matrix product, but it actually comes in quite handy in this case. So here's how it's defined. So if you take some matrix A, right, and then our mask as M, then when you multiply those two, using the Kronecker product, it multiplies this factor with the matrix M and puts it in place. Right? So instead of having the factor in the matrix A, you replace it by factor times this matrix. This is basically the Kronecker product. You take this matrix, each entry of this matrix is a factor, a float number, and when you build the Kronecker product, it takes each number, multiplies it with this matrix, M, and then replaces this factor by this product. So in this way, we get a large matrix as big as our image, filled up with those 8x8 size masks. So we have many masks of the size of the image now. So we just need to have the right size matrix A, and it's easy to see that this just needs to have the size of 1/8 of the rows and 1/8 of the columns, because it will be blown up by a factor of 8 by the mask matrix. Can you see that? So basically we have a mosaic of mask matrices after it. Just like the DCT coefficients, which also appear like a mosaic. Right, so here, mask for the entire frame is NP Kron times of ones of, this is the matrix A, times n. So each time we have a 1 in this matrix, in the first argument, we get a matrix M after this Kronecker product. Yeah, so then MF is the same size as our frame, so that's why I call it MF, F for frame. And then we can use the element-wise division and rounding to obtain our quantization index. So here x divided by m frame gives us, and rounding gives us the index, and for the dequantization we just multiply the indices with m frame. Make sense? So this is just now quantization on the entire frame using our mask. So it's now not just the same coefficients anymore, but different coefficients on each anti-diagonal of our DCT matrix. So now we apply it here to this in this file. So let's take a look at it. So let's do this one here. Gedit this file. So here you can see I'm doing basically what we just saw. I define the different number of bits. So the first few anti-diagonals get a few bits and then nothing. Again, the highest frequencies get nothing. Here I'm building my mask. Mask M. Here I'm building my mask MF. Here I'm computing again the size of the frame. Here I might create an 8x8 block grid. And here I'm computing the Y component of our image. Apply the DCT. And I stick with the Y component. This is again black and white. Here I'm doing the quantization. Here I'm doing the dequantization and the inverse DCT. And then I'm showing it until I hit the QQ. So this is actually not storing anything in the file. And yeah, so there's one component missing here, or one effect that we had in the storing to file. So this is not really storing to file. So what can happen here, which might be a benefit for this one? don't have the ranges. Right? Remember, before we had the range of -2 to 1 for our quantization in order to fit it into 2 bits. Here I'm just doing the quantization, right? But the indices are not limited. I'm not doing any limitation of the indices here. So that's why this might look unrealistically nice. So here I'm computing my number of bits based on assumed ranges. Remember the range that I looked at in the files, but I don't limit it here. Again, for simplicity reason, but to really judge the quality, actually I should limit the range here. Maybe that's something you could try at home to see how it changes the quality if you actually limit the range. And in Python it's quite easy actually. So now we can take a look at it. But keep in mind that the quality might look better than it actually would be with the number of bits that we assumed. Let's see if this works with Python 3. Yeah, this works. So here you can see on the left is the original and on the right is the decoded. Can you see a difference? Right, at first you can see those artificial boundaries right on the board. Here, right there, artificial boundaries. So again, the number of bits for DC seem to be not enough. Right, seems we still need to spend more bits on DC. But other than that, it's actually not too bad. Right? It's actually, you have more or less sharp edges. It's a little bit less sharp, like when you look at here, the edges of the board, you have some blocking artifacts. And in my face, you again have artificial boundaries, but it actually is looking much better than in our previous example, right? Can you appreciate the increase in quality? So we basically tripled the number of bits, but to a big benefit. So here we included now more AC coefficients and using finer quantization according to the more or less according to the contrast sensitivity function. And this gives us actually indeed a big boost on the image quality. So now we don't need so much quality anymore to recognize what's going on. So it's actually containing now much more visible detail in this case. So this should show you that it's really worthwhile to do the quantization according to the quantized sensitivity function. It gives you information about what the eye is looking for. Right? And again, here I dropped all the high frequency coefficients totally. Right? Like most of the coefficients are gone, but these are all the high frequency coefficients, and the eye is not really looking for those high frequencies in an image. Right? So again, we still have quite a good compression, but at a much higher quality now, because we put the bits where the eye notices them. Right? So we put the bits where it's worthwhile to have the bits. We didn't waste the bits on high frequency content, which the eye doesn't see anyway. Right? So this is basically the lesson that you can learn from this example here. Yeah, so it's now indeed significantly better than before, because we took more bits and the contrast sensitivity function into account. Yeah, here we neglected the range clipping. So that's something you could also try on your own to see if you see a difference. Yeah, so this is what I just said. The CSF gives a clear improvement in quality. Yeah, this is actually also how JPEG is doing compression. So here you can actually see the quantization mask which is used in JPEG. And JPEG is basically what your camera is producing. If you have a photo camera or smartphone camera, they basically all produce JPEG, and this stands for Joint Photographics Expert Group. And they have released a standard for image compression and encoding. And yeah, it's also based on splitting the image into 8x8 pixel blocks, like we did. Same thing. Then a 2D DCT of these blocks, and then a quantization of the DCT coefficients. For quantization mask, our quantization mask M is called Q here for quality setting, and for the 50% quality setting, JPEG uses this mask. So it's not the only mask, but this is one of the masks they use for quality setting 50%. And here you can also see the same effect. You have the same values on the antidiagonals. So here you have DC. Surprisingly, DC here is a little bit larger than the next two. Here you have an antidiagonal which have almost identical values. Here's the next antidiagonal. Here's the next antidiagonal, and so on. Right. So here the antidiagonal are not exactly identical, but almost. Yeah, you can also see when you go down to higher frequencies here, this lower triangle here, we have values above 100, which means they're usually rounded to zeros. Values which appear here are usually rounded to zero because they're usually much less than 100. So this using the same effect that the eye is less sensitive for higher frequencies. Yeah, so the smallest quantization step sizes, the size, and the DCT coefficients of the small spatial frequencies on the top left at the highest accuracy. Yeah, towards the lower right, we have higher spatial frequencies, and the quantization step sizes become larger. Yeah, also the number range for the quantization step is quite different here because of an unnormalized image that is assumed. So here JPEG assumes pixels have a value range from 0 to 255, and they don't normalize it like I did it in my example. Right. So that's done because they try to be close to an implementation. And an implementation is always simpler using integers instead of floats. Yeah, here I have the example with the JPEG mask. So if you take a look at it, at this example here, gedit. So here I have my previous mask, and here is the mask from JPEG. So I just, here in this position here, from 36 to 43, I just typed in the values from the JPEG mask, but the rest basically stays unchanged. Yeah, and I also did the normalization here because I'm using normalized values for my image. So now we can execute it. Python 3. Yeah, so now you can see the result for the JPEG mask. And you can see it maybe looks a little bit better, but not so much, right? Interesting. Can you see it? You still see some artificial boundaries and also some blocking artifacts, although less than before. So when you look here at this edge, it looks more clean than before. So you can still see artifacts. So they're actually quite similar. So it comes from the fact that basically this matrix is quite similar to our matrix that we used before. Yeah, And the number of bits in JPEG is variable and depends on the image because it uses Huffman coding with variable length of code words. So that's also different from our coder that we used. We used fixed code word length of 2 bits. Right? But it's actually more efficient to use entropy coding, like Huffman coding, which uses variable length of code words, such that you don't have to limit the range so much. But you can use like values which appear less often, give longer code words to still represent them at the cost of some more bits. Right? So entropy coding, Huffman basically gives short code words to often occurring code words and long code words to rarely occurring code words. Yeah. Yeah, and finally, this is the arrangement of bits. So basically, this is doing it like we did in our example. It's using the zig-zag scan along the anti-diagonals. Right here you can see it starts with DC, and then it appends the next anti-diagonal, then it appends the next, and so on. And then you have a sequence of indices, and you can actually start cutting off from the end to get reduced bit rate without sacrificing too much quality, because at the end you have the least important coefficients. So here in the beginning you have the most important coefficients, and then they are less and less less and less important. And this is how you can get a scalable bit stream by just stopping at some point. So you can reduce the bit rate and also reduce the quality in this way. Yeah, this is, for instance, also used in DVB, digital video broadcast. Yeah, they have this image here from this book, which is actually quite a nice overview about digital TV technology. Yeah, questions at this point? Makes sense so far? So now you saw the basic processing steps for image compression. Quantization and turning it into bits and storing it into file, and then do the reverse steps in the decoder. So now you should be able to build your own picture compressor using Python. Okay then, thanks for your attention and have a nice Christmas break.